So today we are in 1.2, which is titled Analyzing Graphs of Functions. So we've recently learned how to graph different things, and today we're going to use graphs to actually figure out some things that we already know how to do analytically. So the first one of them is to find the domain of a function. Now we know how to find the domain of a function if we're given the equation, like f of x is equal to something, then we can tell what the domain is by using our processes. But this time we don't know how f of x is defined analytically, we just are given a graph. And so we're going to figure out how to figure out what the domain is and the range is just by looking. So again, the domain of a function is all the values of x that are legal to put into my equation. Well, I don't have the equation, so I need to figure out a different way to find it. And so remember that domain is the input, and on our graph, x is the input. So we're looking at the x-axis here. And so essentially we can see the domain here based upon how the spread is across the x-axis. Okay. Now again, we learned when we were doing inequalities that this open circles means that the point actually isn't included, and the filled in circles mean that the point is included. So we need to keep that in mind. Okay. So the domain in this particular function, so we always write from least to smallest. The domain we could state as an inequality. We could write, so the smallest value, so I have -1 valued here, so then this point would be at x equals, because the domain is an x, -3, but it's not included because I've got an open circle. So I would say that -3 is less than x. And then on this side, I want to put the largest value that x could possibly be. And so my x is completely covering. If there were any breaks in my graph here, then I would have to basically kind of stop my domain and pick it up someplace else. So, but my domain covers all of these x values here until I get to x is positive 4. So I'm going to put 4 over here. Now I didn't have an underline, meaning equal sign here with the -3 because it had the open circle. But my endpoint here when x is 4 is included, so I write it like this. If I was going to, typically we write our domains in intervals. If I was going to write it in interval notation like this, I would write it with the parenthesis because that means it's not included. -3, comma, 4, close parenthesis because of the extra line, the equal sign, it is included. All right, so let's look at the range then. Now the range again is the output, right? So now when we're in the range, we're talking about y. So y, right, this is my y-axis. So you want to think of what's the spread, how many different, what's the lowest y value versus the highest y value. Sometimes they're not numbers, sometimes they just keep going on and on and on. But in this particular case, I've got y's between here, if I think of, right, so this is 5 up here. So I've got y values between -2 and +5. So all my graph stays in between there. So I could write that -2 is less than, I've got y this time, is less than 5. And both of these are filled in circles, so that means I can include the -2 and the 5. So if I wanted to write that in an interval, which I also could, I could write it as the range is from 2 to 5, -2 to 5, with closed parentheses because both of these are with the brackets because that indicates closed points, meaning they're included. All right, let's look at a more interesting one here. All right, so we have this particular graph of G, and we want to figure out what the domain and the range are. So for the domain, that's x, right? This is the x-axis, this is the y-axis. I'm looking from side to side. And so if I look over here, it looks like my graph will continue on in this direction forever and ever. And so my domain, basically we would say it goes from -infinity out here because there's no stopping point. And then it seems to have an issue here where there's a break in my graph, see? my graph comes down here, then skips over what is the y-axis, and then ends up back over here. Well, this is the graph, or basically this means that here, x, it's going to skip over x equals 0. Now, my graph doesn't really indicate, maybe my graph isn't perfect here, but actually this graph, it keeps getting closer and closer and closer to the y-axis. It's just not actually going to touch it. So my domain would be, so if I look from side to side, all my x's will be covered except for like right here, this where x is equal to 0 here. Okay, so the way that we write that is we're just going to basically say that x is less than 0 or x is greater than 0 if I have the two separate inequalities. So if we wanted to think of it in interval notation, I would say it goes from negative infinity up until 0 and then 0 to positive infinity. All right, so my range then, I'm looking from bottom to top. Again, my graph looks like it's going to go, it's going to get closer and closer and closer here, and then again it picks up here and goes closer and closer and closer. So again, I've got basically my range skipping over basically this spot in the middle. And so that would be, y can't be 0 either. And so my range would also be y is less than 0 or y is greater than 0, but it just can't be 0. Okay. So I would write this, it would look exactly the same as this. It would be negative infinity to 0 and union 0 to positive infinity in interval notation. Again, if you can write these, it's fine, the inequalities. All right, so let's look at something else that we can decipher graphically. So let's look at, so we've talked about what makes something a function, right? We've looked at the equations of functions or of relations and determined whether or not they're functions. And the primary thing that makes something a function is that every element in the domain is used, and it's only used with one element in the range. So every element in the domain matches up with exactly one element in the range. And so we've talked a little bit about what happens when something isn't a function. So when something isn't a function, then that means that I have two values of x typically that match up with the same y. And so when that happens, we get something that looks like this, because if I think of this point here and this point here that are lining up when essentially is this vertical line here at x equals 2, then when I have these 2 points, both of them have a 2 as their first coordinate, right, as their x coordinate. So this is an indication that I've got 2 matching up with 2 different elements in the range. So I think I've said this before, but we call it the vertical line test. So this is if I end up with some value of x that's going to match up with more than one value of y, which would make it not a function, then visually it looks like these 2 points are on the same line. So we use this idea of a vertical line test that basically tells us that if we can imagine a vertical line passing through our graph, then if it looks like it's going to hit our graph in more than one place, then this is an indication that it's not a function. So this is not a function because I have more than, right, I have more than one y value matching up with multiple x values. So, right, 2 and 3 and everything in between here. The only one that only has a single y value is here. So let's look at a different one. All right, so this is a graph of a piecewise function. We're going to spend some more time graphing them in very shortly, but for right now we're just going to examine this graph. And so we're going to use the idea of this vertical line test, right? We don't know what the equations are. We don't need to. We can still tell if this is a function or not. And so I want to imagine a vertical line passing through any of these pieces, right? Now everything looks really good except for right here at 2, right? So it looks like I've got sort of 2 points here on this line. However, because this piece right here, this point here that looks like maybe 2, 1/2, is an open circle. So while it's attached there, it's not actually a point there. So when it actually does pass the vertical line test. Had this point been filled in, then I would fail. Even if it was at that one, just that one point where they had the overlapping, it would fail. But this, because this point is filled in and this point is not, meaning that this point doesn't actually exist on it, it's just sort of the spot where it starts, then this is in fact a function. All right. So I'm looking at my last example here, okay? And I'm going to imagine a vertical line test passing. I'm vertical line passing through anything. And since it does, it is in fact a function. I used this example because I wanted to show it doesn't actually have to be the entire graph. This probably has some sort of domain. Obviously it has a domain restriction, but the way it's defined, maybe it just doesn't, the points don't exist in here. So this is what the graph ends up looking like. If I was going to state the domain of this, then this piece here, right, from here back, my smallest number in the domain, it's got an arrow on it, so it's going to keep going over and over and over. So if I wanted to state my domain, just to practice here a little bit, because this is a kind of an unusual one, I would say this goes up to -infinity, and this is -1 to -3. So from -infinity to -3, or for x is less than -3, and equal to as well. Sorry, I should use the square bracket there because I've got a filled in point there. Then none of these x values are used until I come here to, oh, we'll call this maybe 3. And so then over here, I'm starting out at x equals 3, but not including 3, so then x would be greater than 3, because then it's going on in this direction, which is going to cover the rest of these x's. So this would say, I would use this notation if I was going to use interval notation. Okay, so that is trying to figure out what a function is without the graph. All right, so I have a couple of functions here that are graphed, and I just wanted to do some visuals of finding f of x equals 0. So if I have f of x equals 0, then that means, right, y and f of x are interchangeable. Let's remember that, y equals f of x. So this is actually saying what x values match up when y is equal to 0. And so if I were going to figure this out, I would plug the 0 in here, right? This is the way we have been doing it. And so this is factorable. I set each one of these equal to 0, and I get x is 3, and I have x plus 2 equals 0, so x equals -2. So that means points on my graph, I plugged in y is 0 here, then I have 3, 0, and -2, 0. So I just wanted to show you that, you know, if you were looking for these solutions, they would actually be these two spaces, these 2 points here, 3, 0, and -2, 0. So if I wasn't given this at all and I wanted to know where f of x was equal to 0, then what I'm really looking for here are my x-intercepts, right? F of x equals 0, solving that, gives me my x-intercepts. These are also sometimes called zeros of a function. All right, so let's look here as well. So I have the square root of 4 minus x squared is my f here, and this is the graph of it. It's a very small, right? My domain, I can kind of see, only goes from -2 to +2 because I'm looking, you know, from side to side here, the horizontal. I didn't label these, but I can do that. Okay, so that's because I've got this underneath here, right? So anything when x is bigger than 2 or smaller than -2, I'm going to get a negative number underneath the radical. So that's why my graph is so kind of small, because if I plugged in x is 3, which clearly isn't a point on my graph, I have 4 minus 9, which is the square root of -5, which doesn't exist in the real numbers. Okay, So that's why my graph is so small. Now, if I wanted to find f of x equals 0, I could solve this. I would have the square root of 4 minus x squared. I have a radical equation, so I square both sides. When I square 0, I get 0 back. When I square this side, I get 4 minus x squared. I can now have a quadratic, which I can just use my square root method by adding this x squared to the other side. I get x squared is 4, and this gives me x equals plus and minus 2 when I take the square root here. Okay? And so that means I plugged in y equals 0, because that's what this means here, y is 0, and I get the 0.20 and negative 20, which shows up again right here as x-intercepts on my graph. So if I wasn't given this and I just wanted to know what f of x equals 0 would be, then I'm looking for my x-intercepts of my graph. All right, so one more thing that I want to talk about while we're talking about graph here is increasing, decreasing, and constant graphs. Okay, so a function f is increasing on an interval if for any x1 and x2 in the interval x1 less than x2 implies that f of x1 is less than f of x2. Now that sounds kind of complicated, but all it really means is that if I have a graph and it looks like this, right, then if x1 less than x2 means that on my number line, right, this just implies that on the number line x1 is to the left of x2. And if a function is increasing, then f of x1 is less than f of x2, it means that the y value for x1 is smaller than the y value of x2. So it looks something like this. So when I go to connect my points like this, it means that my graph has an upward tilt to it. So this is what it means to be increasing, is to have that upward tilt. Okay? So the function f is decreasing on an interval if for any x1 and x2 in the interval, and it's the same exact thing, that x1 is less than x2, meaning it's to the left of x1 is to the left of x2, implies this time my inequality is going in the opposite direction. Okay? So again, pictorially I have x1 less than x2, meaning it's just to the left on the number line, right? 1 is less than 2, it's to the left of 2 on the number line. So that means I have this time my y value for x1 is larger than my y value for x2. So this is an example of something that would be like that. So when I go to connect these, I have a downward slope to my graph. Okay, so this, when my function is increasing, I can visually see that it's moving upward. It's got an upward tilt to it. When it's decreasing, it's got a downward tilt to it. And then this one is pretty straightforward, that if it's a constant on an interval for any x1 and x2, and it doesn't matter which one is bigger, because if it's constant, then the two values are exactly the same, then the y values are equal. And so, again, I'll just use x1 less than x2 again. It just means that the y values are exactly the same and I have a straight line. So that's what these terms mean, right? So constant means that the y values are exactly the same. Decreasing means that I've got a downward slope to my graph, and increasing means I have an upward slope to my graph. Okay. So while we're here, so a relative maximum, while we're talking about increasing and decreasing, and a relative minimum, so these definitions are in your book in 1.2, but really sort of they just mean relative means that it's the lowest point in the area. So minimum means small, right? And so relative minimum means it's the lowest point in a particular area. Relative maximum means it's the highest point in a particular area. It doesn't mean it's the highest point on the graph. It just means the highest point in the area, and the min is the same. So just looking at this graph, okay, these 2 points that I have highlighted here would be considered a relative. This one would be the relative max because it's at the top of a slope. It's kind of at the top of a hill here. This is the relative max. And it is just relative because if you look over here, my graph has pointed upward. So that means that this graph will continue on and on and on and on upward. And so it's not the highest point on the graph, it's just the highest point in this area. So this is what we call a relative max. This point down here, visually, is my relative min, okay? And that is the lowest point in this area. Again, my graph is continuing on and on and on down here. That's what this arrow means. And so it's not the lowest point on the graph, it's just the lowest point in this area. And so if you notice here, something that is going to be important to us much later, is that this relative max comes at basically the intersection of where my graph is going upward. It's got an upward slope, right? So it's increasing here. And then I have my relative max, and then it's decreasing, okay? And then I have my relative min, and then my graph is increasing again. So if I wanted to write my intervals of increasing, where's my function increasing? Then I would say, now we always use rounded parentheses for increasing and decreasing because right here at the top we don't include that point because it's not really going up or down, it's sort of stagnant. It's sitting there at the top. It's like you're at the top of a roller coaster waiting for it to go down the other side. There's always that pause. Okay, so we have my increasing is this piece here, right? It's got an upward slope. Now here's downward, and then this piece also has an upward slope. So if I wanted to connect this for my x values, right? We're always talking about x values when we're saying where's our function increasing. So our x values are increasing from negative infinity, right? All of these out here because these are all going to be way, 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 way down here, right? And they'll be increasing all the way up here until we get to, let's see, this looks like x is -3 here. And so it's increasing from negative infinity to -3, or for x is less than or equal, and not equal, less than -3. I've already said we don't include that top point because it's not increasing or decreasing. So it's just strictly x is less than 3. Let me just take that whole thing out there. There we go. Okay. And then it's also increasing, skips over this part here, right here, where x is 2. So then it goes from 2, and then all my x values on this side are also that way. So for x is greater than 2, I could write this as the union of 2 to infinity as well. So my x values, my y values are increasing when x is less than 3 or when x is greater than 2. So then let's write our decreasing over here. Intervals of decreasing, they go from this point here, right? My graph starts falling until I end up down here at my relative min. So my decreasing goes from x is -3 to x is 2. So we can write that it's between 2 and -3. Or if I wanted to write it in interval notation, it would look like that. All right, so I've got increasing, the relative max, decreasing, the relative min, increasing. All right, until next time.